Biological safety cabinets, or BSCs, are designed to protect laboratory workers and the surrounding environment from pathogens. It is important that everyone working in a BSC understands when they should be used, how they work, and how to use them correctly. BSCs provide effective primary containment for work with infectious material if they are properly maintained and used in combination with good laboratory techniques. A risk assessment should be performed to determine whether a BSC is required for each activity conducted in your facility. In general, a BSC should be used when the activities increase the likelihood of exposure to pathogens, and when the consequences of such an exposure could be serious to either the lab personnel or the environment. For example, a BSC can significantly reduce the risk when handling open vessels of pathogens transmitted via the inhalation route, and when manipulating large volumes or highly concentrated infectious agents. Personnel protection is provided by BSCs through a continuous stream of inward air known as inflow, which helps prevent aerosols from escaping through the front opening. Contaminated air is exhausted through high-efficiency particulate air filters, or HEPA filters, before being released in the environment. Certain types of BSCs also protect the samples from becoming contaminated when working with them. These cabinets use HEPA-filtered downflow air to flush the cabinet interior of airborne contaminants and to prevent unfiltered inflow air from entering the work area. It is important not to confuse BSCs with other ventilated enclosures commonly found in laboratories, such as fume hoods and laminar flow cabinets, which should never be used for personal protection against working with samples containing pathogens. There are many classes and types of BSCs that offer varying levels of protection. Class 1 BSCs provide personnel and environmental protection by drawing room air into the cabinet through the front opening, across the workspace, and then discharging it from the cabinet through a HEPA filter. The filtered exhaust air can be recirculated into the laboratory or exhausted directly to the outside atmosphere if it is hard ducted to the facility's HVAC system. It is possible to work safely with small quantities of volatile toxic chemicals if the BSC is hard ducted. Class 1 BSCs are generally recommended for procedures where total sterility of the biological material is not a critical factor. These cabinets are often used for disposal of infectious waste, placing samples in disinfectant and cage dumping, or activities where infectious material won't be open, but the risks of aerosol generation in the event of a malfunction are high. Homogenization is one example of a process ideally suited for a Class 1 BSC. However, in situations where no Class 2 BSC is available, there are other scenarios where Class 1 BSCs can be considered despite the lack of sample protection. These include processes where the risk to personnel and the environment outweigh the need for sterility. Preparation of tissue sections for formalin fixation, mechanical disruption of tissue with mortar and pestle, addition of liquid samples or homogenates to inactivating agents for downstream nucleic acid or protein purification, and preparation of smears for tuberculosis or rabies diagnosis are a few examples where even without product protection, the likelihood of a negatively impacted end product or test result is low. Other activities such as cell culture, virus isolation, or manipulation of extracted nucleic acids should never be performed in a Class 1 BSC, since the unfiltered air blowing over the work surface is likely to result in contamination, loss of sample integrity, and ultimately unreliable results. Class 2 BSCs provide personnel and environmental protection. However, unlike Class 1 BSCs, they also offer product protection by filtering all air that passes through the front grills before distributing it over the work surface. Class 2 BSCs are further divided into 4 types: A1, A2, B1, and B2, which differ according to inflow velocities, recycling of cabinet air, and connections to building exhaust systems. Class 2 Type A1 and A2 cabinets are the most commonly encountered BSCs in microbiology laboratories. These cabinets recirculate 70% of HEPA-filtered airflow back into the cabinet and exhaust the remaining air out of the cabinet through a second HEPA filter directly into the room. Class 2 Type B cabinets differ from Type A in their higher inflow velocities and direct connection to the building's exhaust system. Class 2 B1s recycle about 50% of HEPA-filtered air back into the cabinet, therefore work with only low levels of volatile toxic chemicals and trace amounts of radionuclides may be performed. Class 2 B2s discharge 100% of HEPA-filtered cabinet air out through the building's exhaust system, and therefore work with volatile toxic chemicals and radionuclides may be performed. While these cabinets provide excellent levels of protection, they have higher electrical consumption, more complex installation requirements, and increased overall lifetime running costs compared to Type A cabinets. All of these factors should be considered when a facility is preparing to purchase a BSC. Class 3 BSCs provide the maximum level of personnel and environmental protection. They are completely enclosed and are kept under negative pressure. These highly complex containment devices are typically reserved for pathogens and procedures where the consequence of a laboratory exposure or environmental release could be severe due to high associated mortality and transmissibility, combined with a lack of effective treatment or prophylaxis. All biosafety cabinets must be certified by manufacturers for compliance with a set of performance standards for BSCs. These can vary depending on the manufacturer's country of origin, but are typically NSF International or the European Committee for Standardization. Ideally, BSCs should also be certified on-site after installation and on an annual basis to ensure that supply and exhaust HEPA filters are functioning correctly and directional airflow is being maintained. Finally, careful consideration must be given to where the BSC is installed within the room. As a general rule, select a location where minimal disturbance to airflow will occur to ensure its maximum effectiveness. BSCs should not be located in high-traffic areas or directly opposite of seated workstations, and a minimum distance must be maintained from other BSCs or chemical fume hoods to avoid disruption of the air curtain. A local risk assessment will help determine a reasonably safe distance to avoid operation collision. Let us conclude this video with a review of the following key messages. BSCs provide effective primary containment for work with infectious material if they are properly maintained and used in combination with good laboratory techniques. There are many classes and types of BSCs that offer varying levels of protection. A risk assessment will help determine which one is best suited for your laboratory and for the types of activities you will be conducting. BSCs should be installed in areas with minimal foot traffic and potential airflow disturbances. Regular on-site recertification ensures proper functioning critical components, including airflow profiles and HEPA filters. Everyone working in a BSC should understand how they work, when they should be used, and how to use them correctly. Knowledge of how a BSC works is a key component to working safely when using them.